Okay, welcome to the online lecture. This is Chapter 20, the second law of thermodynamics. Now, just to review, we already know the 0th and first law of thermodynamics. The 0th law is thermal equilibrium, which says anything that are in thermal contact, meaning touching, for a long period of time, will eventually all be the same temperature. Okay, that's the 0th law. The first law says change in thermal energy is going to be equal to work done by the environment plus heat. And you can change the sign of the work if you talk about the work done by the system, and then it just becomes negative, okay? The second law of thermodynamics has to do with entropy, and we'll address it in this chapter. So here's sort of the general direction that we're going. We're going to talk about the direction of thermodynamic processes. So which way does the time arrow point? Then we'll talk about heat engines, which will bring up specific heat engines like heaters, refrigerators, internal combustion engines, and we'll talk about efficiency in terms of those things. And when we talk about efficiency, we'll sort of work on the Carnot Cycle, which tells us about the maximum efficiency of things. Then we'll introduce the second law of thermodynamics and explore the concept of entropy. All right, so let's start.
Meklab dloi tatuaris gativ ut nosterov mieszastin nodjethe mit mo atrof tur intel ketegel venya figreg nodia kaje ket nastani masimya dwa katu twaim get meklab atu twaim get. Ich nie aus mit der Bahn gehen, ich nie aus mit der Gau. Nein, is on me, that's on Jack. I don't care if I never get back as me root for home team. If they don't do this, a shame for its own root. They say zero out the old game.
So in that video, which of the processes are reversible and which ones are not? Okay, the reversible ones are anything that don't look weird when you run the video backwards. So at the end part, you know, when he's putting on his clothes, right, that doesn't look weird run forward or backwards. You could do it either way. But when you're popping the balloons or when peanuts are flying back into the box, that's going to look strange, and that is an irreversible process. Peanuts never spontaneously jump into a box when they were all over the floor. And just like that, if you look at these pictures, can you put them in chronological order? This is an irreversible process. And we know, just because we have experience living in the real world, that this order goes B, right? So the things that are over here, this is a very ordered system. Then you go C, this is the energy that you're adding to the system, and then you have A, which is a very disordered system. So we know things only really go from ordered to disordered. You're never going to have this, have a tornado, and spontaneously go back to this. Okay? So this is the difference between reversible and irreversible processes. A reversible process is a process that can happen in either direction. So for instance, a collision like this, where you have these particles coming in and interacting, that's considered a reversible process because you can run it the other way and it looks pretty much the same as before, okay? These are both processes that look okay. So before, right? And then after. So you can run this either way and it's going to look exactly the same. Run it forward, run it backwards. That's a reversible process. An irreversible process looks something like that. It can only happen in one direction, okay? Here, before and after are going to be very different. So before, the car is intact. After, the car is all smushed and there's stuff everywhere. You're never going to have a car with stuff everywhere spontaneously do this and go back to being an intact car, okay? It'll take lots of work and it'll never be quite the same. So this is an irreversible process. This is a process that can only go one way. All right, so here's a clicker question that I'd like you guys to think about on your own. Your left and right hands are normally at the same temperature. Is rubbing your hands together to warm them a reversible process, an irreversible process, or there's no way to know? So we'll take a few seconds, pause the video, and think about this before answering, okay? All right, ready? Come back. So it turns out the answer is B. This is an irreversible process, okay? Just like sliding a book across the table, rubbing your hands together uses friction to convert mechanical energy into heat. The impossible reverse process would involve your hands spontaneously getting colder with the released energy forcing your hands to move back and forth. So your hands are never going to spontaneously get colder as the energy released from them getting colder makes your hands rub. That would be really uncomfortable and weird, okay? So let's move on to heat engines. So how do we turn heat into work? All right, work. The main problem in power generation is getting the heat. Once you get the heat, you can turn this into work, okay? And we'll talk about this in a minute. So work can be sort of sorted into useful work, meaning mechanical work, okay? So like turning something or moving something up and down, or electricity, meaning the stuff that you get out of the wall, okay? The way we get this work is either mechanical energy, so wind, water. So what could you think of that would use mechanical energy to convert stuff into electricity? Well, there's like dams and wind turbines, all right? You can also use heat, and the way that you get heat is either through chemical energy, so you can heat stuff up using coal, gasoline, natural gas, hydrogen, or nuclear energy. And nuclear energy just uses nuclear reactions to generate heat. But all of these things create a heat differential. So you create something really hot, and you either create steam that turns a turbine, or you create some sort of flow, okay? These sort of are our global energy problems. So how do we generate heat using these different things? We find that, natural gas and gasoline and coal and nuclear energy, these all have awful waste products that we have to deal with. The key is going from heat to work, okay? So once you get the heat, you can turn it into work. Now, of course, if you use solar energy, you kind of skip all of this, right? Because you can go straight to the electricity form. Although there are several different kinds of solar energy. There's photovoltaic cells where you can actually start creating a current by getting photons hitting a solar panel. But you can also use solar energy, meaning you can focus parabolic mirrors on a particular bit of water and heat it up, and then you're back to heat, right? So you're back over here. Remember, all motorized vehicles other than purely electric vehicles use heat engines for propulsion. Now, where does that come from? Well, that's the combustion of gasoline, and that might charge batteries. Hybrid vehicles use internal combustion engines to help charge the batteries for an electric motor, or they use some sort of gas electric motor hybrid, okay? So remember, work is defined as the integral of under the PV diagram curve, okay? So for instance, work done by a heat engine, if you have your force coming from your gas and your force coming from outside as your environment, right? The environment can compress the gas, and that way your environment is in the same direction as your displacement. This is a compression. But remember, work system is equal to the negative work of the environment. So this is your work system, okay? And we want to change the first law of thermodynamics to deal with engines. So remember, this is the heat added by the system, this is the work done by the system, and this is the change in thermal energy. When we're talking about heat engines, we really want to talk about the work done by the system, because a heat engine is something that actually generates energy and generates either electricity or motion, all right? So when you have some sort of engine, you want to know the work the engine does, therefore the work done by the system. You don't care about the work done outside of the engine because you can't use that, okay? So this is the way we define the first law of thermodynamics for heat engines, okay? Remember, heat transferred into a system is either used to do work or stored within the system as increased thermal energy. And what we care about is the work that these systems do. So let's talk again about energy reservoirs, okay? What happens if you throw this ice cube into the ocean? We talked about this a little bit earlier in chapter 19, but discuss this using terms we used in class. So heat from the ocean water goes into the ice, okay? So that's a positive Q. It melts the ice, which changes the ice, okay? So it changes the way the ice is structured. It's a phase change, and then it also is kind of a volume change. Now, does this change the temperature of the ice? Well, yeah, it goes from freezing to whatever the ocean temperature is. But does it change the temperature of the ocean? Absolutely not, okay? So an energy reservoir is something where you can add or subtract heat from it. Q can go in or out, and it doesn't change the reservoir itself, okay? So an energy reservoir is something so large that the temperature does not change when heat is transferred. So remember, if heat's transferred into a hot reservoir, from the hot reservoir to the system, so we're going to talk about hot and cold reservoirs. If heat's transferred from a hot reservoir to the system, you call that Q sub H. If heat is transferred from a system to a cold reservoir, we call that Q sub C. Okay, so remember, these are always positive. One goes in, one goes out. So this is a different way of treating heat than we've been treating it previously, where heat was either plus or minus depending on whether it was coming or going from the system. Now, instead of calling it plus or minus, we're going to call it QH and QC. Basically, QH is what we used to call plus Q, and QC is what we used to call minus Q. TH and TC are the temperatures of the hot and cold reservoir, and that's going to give you some change in thermal energy. All right? So remember, you can go like this. You can transfer heat into your system, you can transfer heat out of the system, and then Q, just regular Q, is going to be the net heat transferred into the system. Okay, so you have some going in, you have some going out. You subtract QH and QC, and that gives you Q. Okay, so for instance, if heat is transferred into the system from a fire, heat can be transferred out of the system through ice. Okay, hot reservoir is always drawn at the top. The cold reservoir is always drawn at the bottom. All right, and if the temperature doesn't change, what's the relationship between QH and QC? Well, we're not really changing thermal energy. We're not really changing work. So thermal energy is 0. Work is 0. That means Q is 0, which means QH has to be equal to QC unless you have some actual useful work going in and out of the system. All right? So that's where we're at. So if we want to turn work into heat, all right, well, you can do something like this where you take rocks out of the ocean, rub them together, that's work, right? You change the temperature, that's thermal energy, and you throw the rocks back into the ocean. That means your total change in temperature is 0, all right? So we have work, we've converted into heat, but this doesn't do any actual useful stuff, okay? Remember, Q and work are the same. That means work in is equal to QC. This is 100% efficient, but you can't actually use any of that heat or work to do anything, okay? So who cares? All right, let's move on and talk about how we turn heat into work. So let's talk about an isothermal expansion. Looking at the first law, for an isothermal expansion, what do we know about our change in thermal energy? It's isothermal, so that means our change in temperature is 0, which means our change in thermal energy is also 0, okay? Which means Q is going to be equal to the work done by the system, which means in this case, QH is going to be equal to work done the system. And any useful device that transfers heat into work has to return to its initial state at the end of the process. Remember, we want cyclical things, and the initial state means it has the same state variables. So P, V, T, change in thermal energy, okay? So remember, heat goes in, gas expands isothermally, and all the heat is converted into work, but in this case, the gas is going to be in a different state, okay? If you have an isothermal expansion, the temperature stays the same and thermal energy stays the same, but work and heat both change. So heat engines are going to be closed cycle devices that have to return to their initial state, right? Your engine isn't very useful if it can't repeat what it does multiple times. So that means you have to start and end at the same P, V, T, and thermal energy, all right? So remember, a heat engine is a closed cycle device that extracts heat from a hot reservoir, uses some of it to do useful work, and some of it gets returned to the closed reservoir. Okay, remember, Q is equal to QH minus QC. All right, so a closed cycle device means, of course, you start and end at the same state. So on a PV diagram, it would start and end at the same point. That means your change in thermal energy is 0 at the end of a full cycle. So that means your work out is equal to Q, right? This is the work done per cycle by a heat engine. So every time you have a cycle, you get a certain amount of energy out of your engine. And that's going to be equal to Q, which is equal to QH minus QC, okay? So here you have your hot reservoir up here. You use that to transfer heat into your system, which is right here. That heat goes to both work, the output of work, and to your cold reservoir, okay? This is a little bit of waste. This is what's used as useful work. So efficiency, right, is how much of the heat that you put in is converted to work, because obviously some of the heat's coming out and you're not using it in W. So your efficiency is defined as the total work divided by the heat you started with, all right? So efficiency is work out divided by QH. And of course, because we know work is equal to QH minus QC, you can convert it to this. So just convert this to QH minus QC. That gives you QH over QH minus QC over QH. So this is just another way to write the same thing, okay? All right. Now we're going to rank in order from smallest to largest the work out performed by these 4 heat engines, okay? So I'm going to have you pause this, think about it, come up with an answer, and then push play again when you know what your answer is. Okay, we're back. Turns out the answer is D. Now how do you get this? Well, you just subtract QH minus QC, because remember, work out is equal to Q, okay? So here 100 minus 60, that's 40. 200 minus 160, that's also 40. So these two are the same. A and B are the same. 90 minus 60, that's 30. So that means C is going to be smaller than 40. That's going to be smaller than A and B. And 90 minus 40, that's 50. So D is going to have the largest amount of work at 50. These are both going to have 40, and this is going to have 30. So the largest amount of work is D, followed by A and B together, and then C should be the smallest, okay? So let's talk about heat engines. We need something cyclical. So here's an example of a heat engine. We'll start with our initial state, okay? We have a gas in a cylinder with a movable piston. The movable piston has a mass M on top of it, okay? Then we turn up the heat. Heat goes in to our system, right? It goes into the gas, and the gas expands, all right? Now, what's being kept the same here? We have the same mass on our piston in both cases, and we're adding heat. So this is considered an isobaric expansion, because remember, pressure only depends on the cross-sectional area of the piston and the mass of the piston, and these things have not changed from this state to this state. So this is an isobaric expansion. Then you lock this piston in place and remove the mass and let heat go out. Well, if you lock the piston in place, that means the volume can't change, which means this is isochoric cooling, okay? Heat's coming out, so you have isochoric cooling from here to here, all right? Then, if you slowly increase the external force, if you push down slowly, you cause a compression. That's going to be an isothermal compression, and slowly is the key word here, okay? So we have isobaric expansion, isochoric cooling, and then an isothermal compression. So let's draw the PV diagram of what's going on here, okay? The PV diagram should look something like this. So here we start in this initial state, so that's this, okay? Then we use this isobaric expansion. So you can see the pressure remains the same. There's heat going into the system coming from the fire, so that's heat in. And then we get to state 2. Here you remove the mass, okay, lock the piston, then you get isochoric cooling. So heat's going out of the system as you go from 2 to 3, and you can see it's isochoric because it's vertical. Then last but not least, okay, you slowly increase the force, meaning you have an isothermal compression, all right, and heat leaves your system while you do this slowly. So this is your PV diagram for this heat engine. And since you get back to the same state at the end, you can start this all over, okay? So let's try out an example. So we're going to analyze the heat engine to determine the net work done per cycle And then we're going to see the engine's thermal efficiency and the engine's power output if it runs at 600 rotations per minute. So if it goes through 600 cycles every minute. All right, and there's some constants given here. So this is the same one. that looks like this. about ideal gas heat engines. So ideal gas heat engines, that means we're going to use all the stuff that we learned about PV diagrams for ideal gases, and we're going to figure out things like efficiency from our PV diagrams. Okay, so here's a cycle. You can see it's a closed cycle, meaning no matter where you start it, it'll start and end at the same point because it connects all the way around. So remember, work out is the area enclosed by the PV curve. And if you want to do this a little bit more systematically, here's your work done during the expansion. Over here, here's the work done during the compression. When you add your two works up to get your total work, that's your work out. Okay, this is the net work done by your system. All right, so here we want to figure out QH for this heat engine. What we're going to have to do is figure out the area inside the curve. That's the work. All right, and then we know what QC is. That's going to be this plus this, because that's all the heat going out. And we can use this to figure out what QH is, because we have this relationship. We can also figure out the thermal efficiency. All right. So here's another clicker question. We want to know the thermal efficiency of this heat engine. Okay, so I'm going to give you about a minute. Just pause this until you come up with an answer, and then we'll go over the answer. All right, pause. Okay, turns out the answer is A. So that's going to be 0.25. Now, how do we get that? Well, remember, thermal efficiency is just work over QH. All right, well, what's QH? QH is given, it's 4,000 joules. What's the work? The work's going to be the area in here. All right, so that's going to be 1/2 base times height, because this is a triangle. So 1/2 0.1 times about 20,000. So 0.1 times 20,000, that's about 1,000. Okay, so work out, that's about 1,000 divided by 4,000, that's about 1/4. 1/4 is 0.25. That's answer A. All right, now notice efficiency doesn't really have units, and so this is why this thing doesn't have units. Okay, so here's a little review on our ideal gas processes that we've learned, everything we've learned so far in the past few chapters. So don't write this down, okay? This is just a summary that you can use when you're doing any of these problems, all right? And to solve heat engine problems, you want to start by drawing a PV diagram, using PV equals nRT and other equations to calculate your state variables, so P and V and T, and then use those to calculate Q, work, and change in thermal energy for each process. You can calculate QH by adding up all the positive Q values and calculate QC by adding up all the negative Q values, and you can end up with all the variables that we're looking for here. Okay? All right. So let's try applying this. We're going to start with the Otto cycle. All right, so for internal combustion engines, we want to start with the Otto cycle. It's not spelled A-U-T-O, it's spelled O-T-T-O, but it does relate very much to the A-U-T-O Otto cycle. All right, so here's our valve system. Here's our intake valve. Here's our exhaust valve. All right, we start with the intake valve open and the exhaust valve closed. Here's our cylinder. Here's our piston, which moves, and when it moves, it moves this rod also. So piston moves down, it causes a partial vacuum in the cylinder, and a gasoline air mixture enters through the intake valve. Okay? The compression stroke, the intake valve closes, and then the piston moves up. So that compresses your air-gas mixture. Then your spark plug fires. Okay? That means you have ignition, so this air-gas mixture that's now compressed explodes. All right, that power stroke means hot burn mixture expands and it moves the piston back down, which turns the crankshaft. Okay, then your exhaust stroke, the intake valve is still closed, but the exhaust valve opens and the piston moves up. That expels the exhaust and leaves it ready for the next intake stroke, so back over here. All right, the efficiency of the Otto cycle looks like this. It's 1 minus 1 over r to the gamma minus 1. All right, and we'll talk about what that means in a little bit. So here we have how you would draw this on a PV diagram. So this first part, right, here's your intake valve open. You have this compression, all right? This is the part where you have ignition. Here's your power stroke, and here's your exhaust, okay? So ignition and exhaust. Both of those have no change in volume, all right, and you can look at it something like this. So from 1 to 2, the gasoline sprayed in here, all right, it's compressed by the piston. Then from 2 to 3, the spark plug fires. The fuel burns too quickly for the piston to move, so you don't have a change in volume, okay? From 3 to 4, you have hot, high pressure gas that's moving the piston out. And then from 4 back to 1, you have the exhaust valve open to allow temperature and pressure back to the initial values, but we don't really change the volume, all right? So here's an example we'll go through. A small single cylinder auto cycle engine has a PV diagram that you can see below. Point 1 begins at STP, right? So we'll call this STP, the cylinder volume of 500 centimeters cubed. During the compression stroke, the cylinder is compressed to 1/10 of its initial volume. And during the ignition process, 500 joules of heat are added to the system. So 500 joules, that's the QH right here. And we want to know what's the efficiency of this engine, okay? So we're already given QH, that's going to be 500 joules. What else do we need to know in order to get the efficiency? Well, that means we're going to have to calculate the work out, all right? In order to calculate the work out, we're going to have to go through Here's a picture of it. We're not going to go into the great details, but it's similar to the Otto cycle. We just have different, it's just some subtle difference. So like fuel ignition, meaning heating at constant pressure, is significantly different. So instead of having this part up here that's at constant volume for the Otto cycle, you have a constant pressure process for the diesel cycle. Okay, let's talk refrigerators. A refrigerator is basically just a backwards heat pump. Work is done on the system to transfer heat from a cold reservoir to a hot reservoir. So instead of taking heat from a hot to cold reservoir and using it to do work, you put work in and move stuff from cold to hot. Okay? Now you'll say, okay, well a heat engine does this thing over here, and a refrigerator does this. Why can't you connect them and get 100% efficiency? Well, it turns out that doesn't work. And this sort of explains it. So if this guy says, I don't have air conditioners, so I was thinking of just opening up my fridge to cool my apartment, what do you think? Do you think this is going to work? Okay, and the answer is obviously going to be no, but why doesn't this work? Well, what happens outside the back of your refrigerator? What happens to the heat that we take out of the refrigerator? Well, that's expelled into the room, okay? So really, if you open your refrigerator, it'll cool the part inside the refrigerator a little bit, but the amount of heat that comes out of the refrigerator is always going to be bigger than the amount of heat that you pump out of it. So the net heat, the net temperature of the room is actually just going to go up. All right. So let's talk second law of thermodynamics. One statement of the second law of thermodynamics is there's no such thing as a perfect heat engine, because a perfect heat engine would violate the second law of thermodynamics, okay? So no heat engine can ever convert heat completely into work. There's always some waste. There's always something in the QC, all right? So how do we, okay, so we want to know, if we can't get 100% efficiency, how good can we get? And that brings us to the Carnot cycle. So the Carnot cycle is based on a theoretically perfectly reversible heat engine, and it would be the most efficient that you could get for any particular thing. So Carnot efficiency is always the maximum efficiency you can get for anything. And you can see here in the Carnot cycle, we start here and we only use isotherms and adiabats. Okay, so we only use isothermal processes and adiabatic processes, and these things can go either way. So here we have our first isothermal compression. So isothermal compression means that we have QC going out, okay? Then we have an adiabatic compression, which has no exchange of heat. Remember, Q is 0 for adiabatic processes. Then we have an isothermal expansion, so we have heat going in, and then we have another adiabatic expansion, and that means there's no heat exchange, okay? So we drew it one way, but we could definitely draw it going the other way, because all of these processes can be reversed. So Carnot is the same as reversible, and a Carnot engine with the same hot and cold reservoir temps will have the same efficiency all the time. All right, so here is the equation for the efficiency of a Carnot engine, and as you can see, it's just 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. Okay, to get 100% efficiency, this has to go to 0. So the hotter you can make your hot reservoir, the closer you can get to 100% efficiency. But since we know this can never be exactly 0, because this always is a non-zero quantity, and this is always going to be a non-zero quantity, this means this is the best efficiency you can get, and it's never going to be 100%, so it doesn't violate the second law of thermodynamics. So another statement of the second law is that no heat engine operating between TH and TC can exceed the Carnot efficiency. All right, so here we can go through and calculate the Carnot efficiency from the Otto cycle engine from the previous example. All right, so we know that thing operated between temperatures of 273 and 1770 Kelvin, and it had a theoretical efficiency of about 60%. Okay, so the maximum efficiency this engine could have, if you adjust it to all the best parameters, is going to be the Carnot efficiency. Okay, maximum efficiency is always the Carnot efficiency. So we plug those numbers in, and we get about 84.6%. Okay, and so This means that the maximum efficiency you could ever get from an Otto cycle engine with these temperatures is about 85%, and that's bigger than the 60% we actually got. Okay, so can this heat engine be built? I'm going to give you a couple minutes, pause the video, see if you can figure out what you think. All right, we're back. It turns out the answer is no. Now, why is the answer no? Well, what's the Carnot efficiency? All right, Carnot efficiency is going to be 1 minus TH divided by TC. Okay, well, or sorry, TC divided by TH. So 1 divided by TC divided by TH. TC divided by TH, that's 300 over 600, that's 1/2. So 1 minus 1/2, that's 1/2, that's 50%. Okay, well, if you look at the efficiency, that's going to be the work over the heat. So that's going to be 60 joules over 100 joules. So 60 over 100, that's 60%. 60% exceeds the Carnot efficiency of 50%, and therefore you cannot get this efficiency. This heat engine is not physically possible to be built. It violates the second law of thermodynamics. And just for some context, here's some real life efficiencies, okay? So for a coal-fired plant, and for this specific coal-fired plants in the UK, the Carnot efficiency is about 64%. The actual efficiency of the plant, 36%. Okay, remember this one's just based on the hot and cold reservoirs. This one is what's actually observed. Okay, here's a Canadian nuclear power plant. Its Carnot efficiency based on these temperatures is about 48%, observed at 30%. Here's a geothermal power plant. Carnot efficiency is 33% based on the temperature difference, and observed is about 16%. And if you want to check this out, you can find this data on Wikipedia under heat engines. All right. Heat from fossil fuels. Hydrocarbons are burned with oxygen. They give off heat and energy. Here's some of the processes that go through that. All right. So let's talk entropy. Entropy is sort of a measure of order and disorder. So let's think about this in terms of poker. All right. What's more likely, an ordered state, meaning something crazy like a royal flush, or a disordered state, meaning having no pair or one pair? All right. And we know if anytime you've played any kind of poker or any kind of cards, disordered states are much more probable. It's really easy to get a hand that doesn't have any significant pairs. Okay. It's really hard to get a hand that's like a royal flush. Okay. So entropy measures disorder, and entropy measures the probability that a particular macrostate will occur. So here, up here, this is increasing order, right? These things are all lined up. That means that's less entropy, and it's less likely that this is going to happen. Down here, this is pretty random. That means there's more entropy, and it's more likely that this is going to happen, okay? So the second law of thermodynamics, most formally, says the entropy of an isolated system always increases until the system reaches equilibrium, which means if we have this ordered low entropy state, if you take the wall away, this will eventually become something like this. So this is a disordered or higher entropy state. This would be the most likely macrostate. This would be equilibrium, okay? And that would sometimes mean thermal equilibrium. So the second law of thermodynamics means the entropy always increases until a system reaches equilibrium. And what that can be stated as is heat never spontaneously flows from hot to cold, okay? Remember, heat always goes towards, never spontaneously flows from cold to hot. Heat always goes from hot to cold, okay? So here's a question. If a supersaturated sugar solution is allowed to slowly evaporate, we get sugar crystals that form, okay? So sugar molecules go from a solution, a very disordered state, into a highly ordered crystalline structure. And we want to know, does this process violate the second law of thermodynamics? Okay, so think about that for a minute, and then we'll talk about it. Okay, so remember, the system also includes water. So even though the sugar is going from a low entropy state, in a liquid form,